12 million vehicles. That is the precise number of machines dismantled and recycled annually in the United States alone. Why is this industry technically called the car's second gateway? It might seem like the absolute end of the road. However, it delivers a massive stream of steel to the global market, turning ordinary scrapyards into some of the most efficient mines humanity has ever created. One can notice how the world's largest source of recycled steel accumulates here, far from any underground tunnels. At first glance, the metal appears useless, but in reality, each car embarks on a calculated new journey. Once thought to have reached the end of its life, the material transforms into the raw foundation for heavy construction, industry, and even the next generation of automobiles. But this is just the beginning. The process is only gaining momentum. From here, the resources transition into the next phase of deep processing. $48,000 is the initial cost of a car destined for the crusher. After 10 years on the road, the vehicle prepares for a new cycle, but this is just the beginning. How much value can it still hold once it enters the recycling process? It seems the metal is dead waste, but behind that question lies a $60 billion industry each year, where millions of old vehicles are dismantled and crushed. One can notice that if iron ore is a natural mine, then end-of-life cars are an artificial mine without limits. At first glance, it looks like trash, but in reality, this process provides jobs for hundreds of thousands of workers and cuts enormous smelting costs. The burden on the environment drops significantly as the machinery operates. It gets more complex further on. Because the metal is prepared, each recycling cycle saves up to 74% of the energy compared to mining new ore. Systems recover on average 75% of a vehicle's weight, separating steel, aluminum, glass, and plastics. As a result, hundreds of millions of tons of material are reborn every year. Consequently, they continue their journey as buildings, everyday products, and even the next generation of cars. The cycle is complete. 95% is the recycling rate for end-of-life vehicles in the United States, making them the most recycled consumer product on the planet. This cycle feeds the production of everyday goods and the next generation of automobiles. When a car reaches the terminal point of its service life, it is delivered to the intake area of a specialized plant. Technicians immediately begin a rigorous documentation process, recording the vehicle identification number, engine number, year of manufacture, and overall condition. One can notice how workers attach a unique tracking code to the chassis to ensure digital traceability. But this is just the beginning. Why is such detailed data collection necessary for a scrap vehicle? At first glance, the paperwork and photography seem like excessive bureaucracy for a machine destined for destruction. However, this comprehensive record is essential for the plant's operational economics. The uploaded data set allows the entire process to be tracked precisely through the digital management system, providing the calculated basis for assessing the remaining value of each individual unit before physical processing. The inspection focuses intently on components that retain functional life, such as engines, transmissions, advanced electronics, and interior parts. Usable components are carefully separated to supply the multi-billion-dollar market for used auto parts. Vehicles that are heavily damaged or fully worn out, on the other hand, are directed straight into the dismantling process for material recovery. It is visible how technicians photograph specific details for the inventory before the car moves on. It does not end at this stage. One can notice how the vehicles are organized in vast lots across the yard. They stand lined up, ready to enter the processing line in a clear, systematic order. Thanks to this level of organization, every car maximizes its recoverable value. The material is now prepared to contribute back to the economy without haste. 98% is the recycling rate achieved by standard lead-acid batteries found in gasoline cars. This efficiency allows the lead, plastic casing, and even the sulfuric acid inside to be recovered for manufacturing new units. After intake and inspection, the vehicle moves into the processing area to maximize its recoverable value and contribute back to the economy. The first step involves removing the battery, which poses the most dangerous electrical risk. One can notice how technicians extract these units immediately, but this is just the beginning. For hybrids or electric vehicles, the protocol changes significantly. The much larger lithium-ion packs require an even stricter procedure. Technicians carefully detach the modules, package them, and send the units to specialized recycling facilities. Only when the electrical system has been fully removed is the vehicle cleared to move on. Why use a steel probe to pierce the tank instead of standard draining? It would seem easier to simply open the plugs, but the probe connects to a high-pressure vacuum pump to ensure the extraction of gasoline, engine oil, transmission fluid, brake fluid, coolant, and refrigerant gas. On average, an end-of-life vehicle still contains several gallons of fluids capable of causing fires, explosions, or pollution if not handled correctly. Hydraulic clamps secure the frame firmly during this critical phase. Within minutes, the liquids are drained and directed into underground reservoirs. At first glance, this process looks like simple waste disposal, but in reality, nothing goes to waste. Once filtered, most of the recovered fluids are reused to power forklifts, generators, and other equipment inside the plant. It gets more complex further on. Because these recovered resources cut energy costs, the remainder is stored for in-house operations. Throughout the process, pressure sensors, one-way valves, and sealing caps maintain a closed system. It is visible how the equipment prevents vapors from escaping, ensuring safety for the entire line. The dry chassis is now prepared for the next stage of processing. Decades, exactly the time required for old tires to decompose if left in landfills. Once all the hazardous fluids have been completely drained, the car moves into the stage of dismantling its major components to ensure safety for the entire line. Why are wheels usually removed first, since they take up significant space? To the uninitiated, the order might seem arbitrary. In reality, they are easy to process immediately, and their removal clears access to the chassis for complex work. Old tires are among the most difficult types of waste to break down. Instead of dumping them, most are shredded into rubber granules for asphalt roads and playground surfaces, while others are used as alternative fuel in industrial furnaces. The steel and aluminum rims are separated and sent directly to smelters for metal recycling. It gets more complex further on. Next come the windshields and window glass, cut out with specialized equipment. It is visible how these laminated glass panes detach, revealing the PVB layer that prevents shattering. Recycling recovers not only the glass, but also this PVB material, which is later reused in soundproofing materials and industrial coatings. Then the doors are removed. At first glance, a door seems like a simple metal part, but in reality, it combines multiple materials that must be separated. The steel or aluminum frames are cut away for remelting, while the electric motors for window controls, locking systems, and wiring inside are stripped separately to recover copper, plastics, and magnets. The interior follows, with seats, dashboards, and carpets carefully dismantled and sorted. Wiring is often stripped to retrieve copper, while plastics and fabrics are shredded and repurposed into new materials. Everything only gets more complicated. Finally, the engine and transmission, the heaviest and most valuable mechanical assemblies, are removed. Some are refurbished for resale, while others are broken down further to extract aluminum, steel, copper, and even precious metals from catalytic converters. This systematic sequence of dismantling maximizes the remaining value of each component while preparing the frame for the crusher. Before a car enters the final compression, it still carries a mix of non-metallic parts that are difficult to process, from bent exhaust pipes and large plastic panels to tangled wiring. To remove them, the vehicle is sent to the rough processing area, where massive mechanical arms fitted with hydraulic shears take over the job. One can notice how the jaws apply tens of tons of clamping force to rip off any remaining doors, yank out exhaust systems, or crush radiators in seconds. Plastics, foam padding, and other materials that cannot be smelted are discarded on the spot. Thanks to sheer mechanical power, the car's frame is quickly stripped clean of unwanted parts, far faster than manual disassembly. This cleaning step acts as a coarse filter for the entire line, eliminating materials that could ignite, contaminate the recovered metal, or damage the crusher itself. After only a few minutes under the hydraulic shear, the vehicle's structure is reduced to a neat steel and aluminum shell, ready for compaction with maximum efficiency and safety. 150 to 200 tons of hydraulic force descend upon the bare steel frame inside the massive press. The structure, originally spanning more than 4 meters in length, buckles and folds under the immense pressure. One can notice how the metal collapses into a compact block, its volume reduced to just a tenth of the original state. But this is just the beginning of the densification process. Why transform the vehicle into such a specific shape before shredding? It might seem easier to feed the hollow frame directly into the cutters, but without this compaction, the loose structure would cause the shredder blades to slip, reducing efficiency and increasing wear. Different technologies achieve this goal based on the specific needs of the facility. The car baler compresses the frame into a dense, cube-shaped bale, which is easy to stack and transport. Modern industrial balers operate with a rhythm of 25 to 40 cars per hour, serving large-scale operations. The car flattener, on the other hand, presses vehicles into flat sheets only a few dozen centimeters thick. At first glance, the flattener seems less sophisticated, but in reality, it offers distinct advantages in speed and lower investment costs. The process is only gaining momentum. However, flattened cars are less dense than bales, meaning the later shredding stage consumes more energy to process them. The shear baler provides an alternative, both compressing and slicing the vehicle into short, manageable sections. Although its throughput is lower, it opens a direct path to smelters, sometimes skipping the baling step entirely. Baling packs goods for storage, flattening rolls them for transport, and shearing chops them for remelting. Dense steel bales travel into the high-capacity shredder, which serves as the mechanical heart of the entire line. It is visible how massive steel shafts with interlocking teeth rotate in opposite directions inside the chamber. The thunderous clash of metal fills the air as the machine tears the compressed block apart within seconds. A car that once occupied a full parking space turns into uniform fragments of scrap. It does not end at this stage. Because efficiency is paramount, a modern industrial shredder processes 100 to 150 tons of steel per hour. This allows the facility to handle hundreds of vehicles each day, transforming mountains of scrap into raw material ready for smelting. One can notice how the mix of metals and non-metals travels along the sorting line after shredding. Powerful magnets extract carbon steel first, lifting it from the stream. Eddy currents deflect aluminum and copper to the side, separating them from the flow. Plastics, rubber, and fabric residues fall away to be discarded. Thus, the recovered steel is compressed into bundles, fully prepared to re-enter the production cycle. 1600 degrees Celsius is the critical threshold awaiting the compacted bales of steel in the next stage of recycling. What was once an old car frame, now shredded and bundled into standard blocks, enters the electric arc furnace to face an inferno. Graphite electrodes descend to unleash currents of tens of thousands of amps directly into the scrap. A blazing arc strikes like artificial lightning, turning the solid metal red hot before it collapses into a liquid pool. One can notice how the solid shapes vanish completely into the glowing stream. Why are lime and flux introduced into this boiling cauldron? The molten steel appears ready for casting at first glance. But without these additives, impurities would remain trapped in the metal, weakening the final product. They draw out unwanted elements, forming a layer of slag that floats up like silvery foam for removal. Oxygen lances simultaneously burn away carbon, while spectrographic analysis monitors the alloy's composition to ensure it meets exact specifications. From a chaotic mass of scrap, a sea of pure steel emerges, but this is just the beginning. The melt flows through sealed troughs into the continuous casting line without delay. Water-cooled molds seize the liquid metal, freezing the outer layer instantly to form a hardened shell. Inside, the core remains molten and dangerous. Rollers carry the strand forward, cooling it gradually along the entire length of the line. It seems like a simple cooling process, but thermal saws must cut the continuous strand with perfect timing. Massive square billets and flat slabs, each weighing several tons, are numbered and logged into batches. From here, the glowing red steel surges into the hot rolling mill. Dozens of heavy rollers press, stretch, and bend the material with immense force. High-speed cameras and laser sensors track the thickness every millisecond. The process transforms a rough block into uniform sheets, effectively sculpting muscle into metal. However, the transformation does not end with shaping. High-pressure nozzles envelop the steel in a white mist of water, rapidly lowering the temperature to prevent cracks. Powerful fans blow along the coils to stabilize the internal structure. Finally, ultrasonic sensors scan for hidden fractures, while mechanical testers verify tensile strength. Only approved coils are stamped, ready to serve hundreds of modern industries. Hundreds of tons of force initiate the transformation of an old vehicle. Why is dismantling required before the press operates? It seems faster to crush the car immediately, but safety mandates draining fuel and removing parts to prevent explosions. One can notice how hydraulic presses compress the stripped chassis into a compact block, but this is just the beginning. The thunderous roar of the shredder awaits the metal cubes. It is visible how rotating hammers smash the scrap into pieces. Conveyor belts move the mixture where magnets and eddy currents separate steel from aluminum. Advanced sensors sort the remaining materials. Transition to the next level. At first glance, the fragments look like waste, but in reality, they are the ingredient for new steel. The scrap melts in the furnace to be reborn. Hot rolling shapes the glowing material, and cooling systems lower the temperature for inspection. And this is not the limit. Because this utilizes scrap, it cuts energy consumption and eases strain on resources. Therefore, the process fuels a multi-billion-dollar industry while avoiding waste. Clean, durable material serves construction and the making of new automobiles. The steel is now ready to enter the next cycle of the economy.